where they're going to move. There's no net force on any excess charge here. And the reason why we have to do that first is we need to figure out what is the charge on the inner surface. So working backwards from what we did last time, I create a Gaussian surface that's 4 centimeters from the center. Because you can't have too many dots in one drawing. If the electric field where the green surface is, and it's supposed to be green, if that electric field there is 0, then what is the total electric flux?
Also 0.
And therefore, what is the enclosed charge?
Also 0.
I hope so, unless Gauss has been lying to us. If the electric field is 0, the electric flux is 0. The electric flux is 0 through a closed surface, then the enclosed charge has to be 0. Therefore, what is the charge on the inner surface here? If it's an electrostatic equilibrium, the excess charge will be on the surface, or surfaces in this case, because I have 2. What is the charge on the inner surface?
Is it 30 nanocoulombs?
No. Let's run with that for just a second. It's not the right answer, but let's run with it. So on the inner surface, you speculated 3 nanocoulombs. And that is the excess charge, but it doesn't work out that way. And I've got a -4 nanocoulomb charge there. I do my Gaussian surface at the 4 centimeter mark. Let's apply Gauss's law. The enclosed charge over our constant. What is the total enclosed charge in my Gaussian surface?
-1 divided by 8.85.
Which tells me my electric flux is not 0, despite the fact that I know I'm inside a conductor there and it has to be 0.
Okay, so that's why that doesn't work.
So therefore, what is the charge on the inner surface?
0.
If we have 0 there, then what's the total enclosed charge?
Oh, it would be -4. So it has to be -4. Wait, no, sorry, +4.
It has to be +4.
Okay, that makes sense.
For the total charge to be 0, yes, ultimately, it is an equilibrium. So this is 4 nanocoulombs. Now we use Gauss's law in order to show that had to be true. Hopefully you'll get faster and you'll eventually go, oh, it's -4 in the middle, I must have +4 here. The electric field is 0. So if I have 4 nanocoulombs there on that inner surface, how much charge do I have on the outer surface?
You wouldn't.
Not hearing?
I don't think you would have a charge.
No, we definitely would have a charge. Let's think back to the original rules we had over there when I set up the problem.
No. Oh.
Can we set up another Gaussian surface at the 7 centimeter mark?
We could, but let's do we don't need to do that in order to figure out the charge on the outer surface.
Would it be -1 nanocoulomb?
It would be. And how'd you get that?
Because on the inner surface we have 4 and the total excess charge is 3 and 4 minus 1 is 3.
Yep. We still have this restriction right here. I know what the total excess charge is. I just happen to have 4 here on the inside, so the question is, what do I have on the outside in order to give me 3? So that's -1 nanocoulomb. The sum is what the problem stated I had. So I got -4 here, nanocoulombs, I got +4 here, and I've got -1 here. So I'm at 7 centimeters. Now we create the Gaussian surface. What's the total enclosed charge?
Cause it's still -1.
It would be -1. Those would cancel out, left with -1, or 3 plus -4,
Yeah,
-1.
That's how I got it.
Slightly faster to do it that way than to think about all the surfaces. Now, the other bit, the other shortcut that I was hoping people would see, not only early on when I asked about one of the shortcuts, since I can ignore, got the spherical symmetry, since I can ignore the charges on the outside, what charges I have on the inside, I can treat like a point charge. So if I get the spherical symmetry and I'm out here, I just think that, oh, I have an electric field of some point charge with a charge of, in our case here, -1 nanocoulomb. So I could go through Gauss's law, or treat it like a point charge in the middle there, in my electric field, KQ over R squared, R hat, which is 9 times 10 to the -9, times -1 nanocoulomb, times 10, 9 times 10 to the 9th, -1 times 10 to the -9th, over 0.07 squared, R hat. And we get some number that would just be spectacular. Whatever that is.
I got -1,836.73.
Negative 1,800.
36.73.
I got that too.
Same.
And that's nano, yeah. Thanks for that.
And just to make it official. -186. 36.73 meters per coulomb.
Dr. Fox, you said the last little shortcut was you can treat charge inside of a conductor like a point charge.
If I have spherical symmetry, if I'm outside some spherically symmetric distribution of charge, I can treat that spherically symmetric bit of charge like a point charge in the middle.
Okay. Okay, makes sense. Thank you.
In 252, I will go through it's a long, hour-long derivation to eventually come out with, hey, we could have treated it just like a point charge. Or if I do the inside, you go through an hour long and you end up with 0. Which some students find frustrating to come out with something so simple. But I think it's kind of cool where you do all this stuff and it just comes out to a very simple answer. Questions before we officially start 19? And let's start on 19. I see some people still looking at the board. Is there anything I should not erase it immediately? All right, all's well and good. Chapter 18, we've looked at these two major vector quantities. When dealing with charges, we've dealt with the electric force and electric field. But what about the scalars? Haven't we left them out? Yeah, we got a little bit of a soupçon of scalardom with the electric flux, but surely there's more. And you're right, there is more. We're going to go to the classic physics analysis using scalars. In other words, we're going to talk about energy. So if I asked you, what is the formula for potential energy, what would you say?
1/2 mv squared.
Potential energy.
Oh, there's a U in there.
Right.
It depends.
It depends. And a V.
Or which one?
That was the response I was hoping for, but it depends also works. If you recall, for every conservative force, there exists a potential energy formula. Shorthand for what I just said. Since the electric force is conservative, there is a potential energy formula. Since F sub E is conservative, there exists a potential energy formula for energy. Or, no kidding, a potential energy formula for electricity. I guess I flip back and forth. I guess I usually use a lowercase e there. Now, the derivation is something that I'm going to just have to give you. I am going to parallel it to gravitational potential energy when the acceleration due to gravity is not constant or unknown. If you recall, the formula for gravitational potential energy, or the formula for gravitational force, the generic formula, you got big G, mass 1, mass 2, over R, the distance between the two masses, or center of masses, times R2 hat. The potential energy formula, gravitational potential energy formula, negative big G, mass 1, mass 2, over R. This is something that we did last semester. We used this ultimately when we did the classical derivation of the Schwarzschild radius. In other words, how small does an object need to be to create a black hole?
Quick question. For some reason, I'm remembering that when we did the potential energy formula for gravity, it was something like 1/2 mgh or something. Is that not the potential energy formula?
All right, so this is the generalized formula. If little g is approximately constant, then the force due to gravity is the weight, which is mg. And the potential energy formula in this case is mgh. No 1/2 in there. But this assumes that little g was constant. The reason I'm using this one right now is because this formula is very similar to the electric formula, which was K Q1 Q2 over R squared. I can't really derive the formula without using calculus, but I at least wanted to hopefully bring back some memories of what we've done in the past. The big difference is the minus sign is going to be gone, and the letters are different, but U sub E is K Q1 Q2 over R. Brooke?
Just to clarify, you said that over here it's every electric force there's a potential energy formula, or was it?
Every conservative force has a potential energy
Okay,
formula.
thank you.
Other questions before I talk about the minus sign?
The license came from the derivative, right?
Right. And with gravitational force is always an attractive force. The minus sign actually comes out because it's always attractive, and the masses are always positive. Whereas over here, it's attractive only if the charges are opposites, in which case one of them is going to be negative, and so the negative would show up. if it's if we're dealing with an attraction here. Or potential energy would be a positive number if we're not, if it's a repulsion. I also want to point out that the potential energy formulas, when you go through the derivation, and we did it for this also, what we actually did when we derived this is we came up with negative U final plus U initial is equal to negative mgh final plus mgh initial. When we did the derivation, we came up with this, and then the question was, what is a formula for potential energy that would make this work?
Is this the one where you had that little plus K that we never used?
Yes. Oh, no, we did use it.
Oh, I forgot entirely.
No, it was justification for the always because I said so, or because so-and-so said so. That plus K there allowed us to do that. So what Anna is referring is mgh works plus any constant. I can always tack on a constant. Because when I subtract, the constant's just going to drop out. This constant here allows us to establish 0 wherever we want. Or, as a problem writer, wherever I want. There was a problem, occasionally I do this, because sometimes I forget, sometimes it's more of a matter of, I wonder who's going to see the easy answer. I set up this problem, and I said, what's the potential energy of this system? And the simple answer, if I don't define where 0 is you just go, oh, the answer is 0 joules, because I'm saying that's where it's 0. Now, I have done that not thinking about that, just going with the standard brainwashing. Typically, you establish your potential energy, your electric potential energy, at 0 when R is equal to infinity. So when you're infinite distance away, R becomes huge, my fraction goes practically to 0. For the math purists, the limit as R goes to the limit as R goes to infinity of U of E. Or for the physicist, we let R equal infinity and U goes to 0. Let's just do a quick plug and chug here. Let's establish, I'll just write it the way we would traditionally write it. Let U sub E equals 0 at R equal to infinity. 5 microcoulombs and 3 microcoulombs, and let's put 0.07 meters away from each other. What is the potential energy in this system? Well, I've got 2 charges there. It's straight up plug and chug. 9 times 10 to the 9th. Times 5 times 10 to the negative 6th, times 3 times 10 to the negative 6th, divided by 0.07. As in the first semester course, at some point I will be writing the potential energy formula out, and I will put out of habit R squared on the bottom, and please correct me. Potential energy formula is not squared in the denominator.
I got the same answer.
Yeah, you said you got the same?
Yes.
Let's finish it off. I think somebody just mumbled it. Maybe I'm just hearing things.
I mumbled, I don't know what the units are.
Coulombs?
What's that?
Is it just coulombs?
Oh, not Coulomb.
Wait, potential energy.
Alright. This coefficient right here is Newton meter squared per Coulomb squared times coulombs divided by meters,
Newton meter? Wait.
which is, if you wrote down Newton meters, that's correct, but
Yeah,
what's the one word?
what is that? I don't remember.
Oh, yeah.
Shoot, what is that?
Bueller?
Is it joules?
It's
There
Joule.
it is.
Although Newton meters is, again, is the correct answer. Alright, so let's add to that. So I got 5 microcoulombs and the 3 microcoulombs, and let's keep it the same distance apart. So 7 centimeters apart. And then let's stick a charge right here of -4 microcoulombs. And let's put it, where have I not used yet? So 6 centimeters and 8 centimeters. How would you find the gravitational potential energy of this 3-particle system? Or what would you speculate?
Kind of looks like you have to break it into components to account for the direction.
Fortunately, we don't.
Oh, good.
We're not dealing with vectors here. The advantage of energy, we don't have to deal with the vectors. The disadvantage, we're not dealing with vectors.
You said how would you find the gravitational potential energy of that one?
Yes.
Can we use Pythagorean theorem?
Ooh, you're going way too complicated.
You just do this process for the one set of points and the other set of points and then sum